I would like to go through two examples with you today over this p-value stuff, and at the same time that we do the p-value, actually draw comparisons to the critical value information as well. So we can see the link between them, but obviously note that when we report things, we can either report with critical values or with p-values. Coding-wise, if I'm writing a package for a statistical package that the user types in the data that they have and they choose the test that wants to be done and all the information that is spit out to them that we are doing by hand or with our calculators or Excel, those packages are going to report the p-value probably 95% of the time, okay? Simply because it's less coding, because they don't have to do anything with alpha in order to do that calculation, okay? If they use critical values, they have to take alpha, change it to a z-score, and that's one more calculation, one more level of coding that has to be done. So p-values are what are usually presented. Yes, Riley. Excuse me? Can I hear an email? You'd have to actually read. Now that we have that. So this says a study found that the average stopping distance of a school bus traveling 50 miles per hour was 264 feet. So the group of automotive engineers decided to conduct a study of its school buses and found that 20 buses, the average stopping distance of these buses traveling 50 miles per hour was 262.3 feet. Standard deviation of the population was 3 feet. Just to claim that the average stopping distance of the company's buses is actually less than 264 feet. So using level of significance of 1%, use the p-value technique. I should also add in here, because we only have 20 buses, I should have in here that the population is normally distributed so that we can use z-tests, okay? So we need to identify the hypotheses and the claim here. Yes, Peyton?
Is this like a real study?
This is real stuff, yes.
So how do they
So what they'll do if, let's not go with buses. Let's go to, so Honda has a racetrack out in, when you go down by Marysville. They've got a racetrack behind their plant. And they will do their testing out there. So they'll take these and they'll set them at 50 miles per hour, and then they'll automate a stopping instrument to make them depress the brake at the same speed every single time, and then measure, okay, so put the brake here, how long did that take for them to come to a full stop? So they'll do this in almost like a controlled environment where they'll take these cars, they'll take these buses, and they'll run them through. But you're right, so the depression of the brake will determine how those calipers grab the disc brakes, whatever they are, and slow the bus down. So it'll be something like that will have to be a variable that they control in the study. Does that make sense? But this is something that people are interested. Okay, I want my bus to be able to stop, right? If you go to sometimes cars will use this type of data or study to maybe produce advertisement or produce marketing. A lot of times you'll see the antithesis of this. A lot of people want to buy a car that's fast, right? So it says this car accelerates from 0 to 60 in X amount of seconds. It's really the same idea, except for instead of stopping, we're accelerating. So we want to identify the hypothesis, the null hypothesis, and the alternative hypothesis in the claim. I think the way that I've worded this, the claim can kind of be fuzzy, but we should be able to identify the hypotheses pretty easily. The null hypothesis always includes what symbol? Equality. Okay? So as we read this, talking about the average stopping distance, we have that. Okay? We have this blue statement here. It says a study found that the average stopping distance of a school bus traveling 50 miles per hour was 264. To test the claim that the average stopping distance of the company's buses is actually less than 264. So I guess in this one, I think I'm thinking about the next question we do. I do establish what the claim is here pretty obviously, right? So mu is or was 264. That's what we're arguing as being the accepted stopping distance of this brand of school bus. Okay? The alternative hypothesis is saying that it's less than 264. So less than 264 would be that, and that is obviously then the claim. Is that okay? So we want to test this. We want to see if we should accept this, or I guess fail to reject it, or reject it. Okay? And does that then produce evidence to either support or not support our claim? So when it says determine the test statistic, that is saying in your data, standardize your data using this idea because of the structure of the scenario. We know it's a population that is normally distributed. We know we're doing sample means, and we know the population standard deviation. So this is going to be the formula allows us to standardize that. X bar for our 20 buses was 262.3. What's mu? 264. It's always found in that null hypothesis. So it's 264. Standard deviation, they said, was 3 feet. And we'll divide that by root 20. And that will give us our test statistic. So we need to calculate that. So let's see here. So 262.3 minus 264 divided by 3 divided by square root 20, and it gives us negative 2.53. Negative 2.53. Is everybody okay with that? All right. The next thing it says determine the p-value. Well, the p-value is attached to the type of test that we are doing. So when we look at this here, is this a left tail, right tail, or two-tailed test? It's a left-tailed test. So our p-value is going to be the area to the left here of where our test statistic kind of creates that separation, okay, of the area to the left and the area to the right. So we need to find that p-value. So there's a couple different ways of doing that. We can go to a z-table. Okay, we've seen this multiple times. Go to negative 2.53, so it'd be this box right here, and we get 0.0057. Okay, using Desmos. Now, Desmos, you just got to be careful with this because for whatever reason, and they're really the same calculator, but this scientific calculator does not have the stats functions. It doesn't have a lot of the functions that this calculator does. Okay. So here I want to type in normal dist, leave the parentheses vacant, find cumulative, and we're going to leave that as, because the left tail, we want that to be negative infinity, and this will be the negative 2.53. And you see there that number is identical to the number that was pulled out of the chart, out to 4 decimal places. If I zoom in on the table or the graph here, whoa, you can see that it starts shading to the left. Okay, but if I'm zoomed out, obviously in that scale you can't see the shading, but it does exist there. Okay. So that's our p-value. Is that okay with everybody? Okay. You can do the same thing with Excel. So with Excel, we're going to go equals norm.dist. We'll type in our negative 2.53. And then the rest of this is always standard 0, 1, true. And there's the same 0.0057. Okay? So that's our p-value. So a lot of times you'll see it written this way: the probability that you get a test statistic that is more extreme in the left tail than negative 2.53, the probability of that happening is 0.0057. Okay? So the probability of getting data from 20 buses that is more extreme than that is 0.0057. Okay? Now, our alpha in this case, it says decide to reject or not reject the null hypothesis. What we're going to do is we're going to take our p-value and we're going to compare it to our alpha. So our alpha is 1%. Okay, so our p-value is 0.0057 and our alpha is 0.01. And you're always going to, I suggest this to always put the p-value first, because that's how we decided up here in the notes. Okay, notice that the p-value always comes first in these decisions. Okay, so if I look at my p-value, okay, how does this p-value relate to that one? They're obviously not equal. Is the p-value more or is the p-value less than 1%? It's less. Okay, so when that is the case, when your p-value is less than your alpha, you're going to reject the null hypothesis okay? We would say there is evidence to support the claim that the average stopping distance is less than 264 feet. Okay? Now, eventually, what we will do is have an idea of saying, okay, it is less than 264, but is it practical? Okay, meaning, am I the bus manufacturer? So less than 264, we might have data here, and we have to do a little bit more investigating, but we might have data here that suggests that the actual difference between the two areas is minuscule, to where we're just to the left of a critical value for rejection. So we might reject, but maybe we see that the actual distance for stopping should be like 263.5 feet instead of 264 feet. Well, if I'm marketing brake pads or marketing this bus braking system or whatever, and I see that it is less than 264, but only by 6 inches, is that a really big deal? That kind of makes sense? Okay, so that would be a huge deal. But if I could say that, hey, we stop 30 feet shorter than competitors' buses, okay, maybe then a school board would be interested in that, because potentially that could save lives if a bus were in an accident or something like that, or potential accident. Does that make sense? But that 6 inches, probably not a practical value, even though we reject the null hypothesis, probably not a practical value to market. When I left this on Desmos to kind of show this, when we talk about the alpha of 1%, okay, so going from 1%, so if I go equals inverse, I guess norm.inv of 1%, so 0.01, 0, 1, a negative 2.32, negative 2.32. So I'm going to put that on top of what we're dealing with here. So you can kind of still see the red region here, right? okay? And you can see the blue region, okay? So the blue region is the region that was defined by alpha. And if our red region is less than that, our red region, all of it is encapsulated inside the blue region, that's our p-value. So that would be the image that says you're going to reject the null hypothesis. Because right now we're saying that if this value here is 2.3, and that creates the region for rejection, and we got negative 2.53 here, then that's in the rejection region, just like we do with critical values. Okay? But if things were flipped around, and our red was over here, okay, we would basically say that the p-value, that area, would be greater than alpha, and that would allow us to fail to reject. Okay? But this image here is showing you that with this red area here, that is less likely because that's a more extreme set of data. The probability of getting a more extreme set of data is 0.0057. Does that kind of make sense? All right. The next one has a lot of data that needs to be processed. Okay, so I've kind of done this for you, so you're not going to have to go through and actually find the average of that stuff. I'll show you what you would need to do if it was all left up to you. But this is a company that says you recently received a job with a company that manufactures automobile anti-theft device. Conduct an advertising campaign for the product. You need to make a claim about the number of automobile thefts per year. So the population of various cities in the United States differs. You decide to use rates per 10,000 people. So the rates are based on the number of people living in the cities. It says last year's study showed that the theft rates of 10,000 people were 44 vehicles. So you want to determine if it has changed. Okay? So when I write that phrase, you want to determine if it has changed, we're ultimately making the claim that things have changed. And that's why I said earlier, and I misspoke on the first question, that I thought I wrote the first question where the claim was kind of fuzzy. That's the claim right there. Okay? When it talks about like 44 vehicles being stolen for 10,000 people, so if you have a city that's 10,000 people, then 44 vehicles on average are getting stolen that year. If you have a city that's 20,000 in population, then the idea is that you have 88 cars or 88 vehicles in that population being stolen that year. Okay, but this is what they're going to basically be asking us to do in almost every situation. These 10 things when we come across a study like this. Okay, it says what hypotheses would you use? Okay, so let's write those down. I'm going to write my hypotheses. We're going to have H sub 0 and H sub 1. Okay, remember that 1, that subscript of 1 can be an A if we want it to be an alternative hypothesis, or a 1. Those are interchangeable. So we're talking about mu again. Okay, what is the current established accepted mean for car thefts per 10,000 people? 44. Okay. And that may be a fact that came from, maybe this company does this study every year, every 2 years, every 3 years, something like that. So maybe that information, that 44, comes from a previous study that they've done. Okay? We are wanting to say, so you want to determine if it has changed. Does it say a direction that we want it to change? No. So what symbol do we use down here on the alternative hypothesis? Not equal to. Okay? And we already talked about the wording and why we would make this the claim. Okay? So set up the hypotheses and then establishing the claim. That's step 1. Step 2. It says, is the sample considered small or large? Okay, the sample is the cities that we're looking at here. It says we have 36 cities. In statistics, with central limit theorem in mind, is that considered a small or large sample? That is considered large. Okay? Large. The central limit theorem says that if you're above 30, then that's considered large, which then guarantees normality, which is what we want. Okay? So because of that, then the assumption that we are making about the variable, and this is one that I'm just going to tell you what has to happen here, because we're going to use we're looking at the mean, we want to use the Z distribution. So the assumption that we have to make here is that our information comes from a normal population. Okay? There are, it's called like a normal QQ test. At some point, if we have some time later on, we'll go through and show how we can take our data and plot our data on it's called a QQ plot. And if it stays within bands on that QQ plot, you can argue that the population is normal. Because we've gone through that, almost every question throughout the year says, assume that the population is normal, right? Well, now you get in because I always get in the situation or the thought, okay, well, somebody's telling me to assume that. What happens when somebody that doesn't tell me to assume that? How do I get to this point of saying that I can actually use this property? So we would do a QQ plot to help with that. So we want a normal population. 5 says, would you select a 1 or 2-tailed test? What are we going to choose here? 2-tail, why? Okay, so the not equal to tells me why. Okay. It says, what critical values would you choose? Okay. And here I said answers may vary. Nowhere in this problem does it tell me how to choose my critical values. Okay. Remember, critical values are predicated off of a level of significance. And nowhere in the problem does it tell me a level of significance. Does that make sense? And I did that intentionally for when we are done with the problem so we can make some arguments. But usually, a critical value that you would use would be 10%. Or you could use, I guess, a level of significance of 10%, a level of significance of 5%, and a level of significance of 0.01%, or 0.01, which would be 1%. Now, those are not the critical values. Those are the levels of significance. The critical values, if you remember, those are then found by using this. Okay? If I want 10%, and this is a 2-tailed test, right? So I'm going to take 10%, and I'm actually going to divide it by 2 because of the 2-tailed aspect. So negative 1.64. And because it's a 2-tailed test, I would be plus or minus. Then we're going to do the same thing. But instead of 0.05, we'll cut that in half. And we get plus or minus 1.96. And then we'll do it one more time with 0.005, which is half of 1%, and you get your 2.58. So those values, as they're plus or minuses, those are your critical values that you would choose per whatever alpha you chose. Does that make sense? Okay. So what p-value would you realize? Okay, now the p-value that we're going to work with here is actually going to, we have to run through our Z statistic. Okay, so these two, 6 and 7, are kind of working together here. So let's find our Z statistic, which is going to be found by x bar minus mu over sigma divided by root n. And this is where, on your own, you would have to process this data. So I think I have it here. Okay. So I got that data in. All I need to do is x bar is the average of that, right? We've done, for the most part, when we've done averages, we've put all our data in a column. You don't have to. You can put it in a table like this and just select the whole table, and it will know what to do with it. 55.97. 55.97. So that is x bar. Mu was 44. Sigma, I tell you down here, it's 30.3. And again, that's a number that generally is going to be difficult for us to know. And you're going to find out that when we get into the next section, the t-test, because we very rarely know this, we might only know this from previous testing, previous studies, the t-test is actually a lot more of a prevalent test than the z-test. And then our sample size was 36. So we can standardize that. Let's see here. $55.97 minus 44 divided by 30.3 over the square root of 36. 2.37. Okay, 2.37. All right, so let's just think about something real quick, because right now, if I look at 2.37, that's a two-tailed test. So I'd be looking at positive 2.37 and negative 2.37. That's my test statistic. That's the Z from the data. Z from the data. Okay? If I were to look at, comparing that to plus or minus 1.64, 1.64 and negative 1.64 would be those two locations. Does that make sense? So if I'm looking at alpha being 10%, this would tell me that I would reject the null hypothesis, because my test statistic is to the left of my alpha values, which dictate my critical regions, right? Does that make sense to everybody? If I went to a 5% alpha, all that's going to do is basically move these critical values a little bit further to the right and left respectively, but they're still going to be in positions where my Z statistic is still falling in the critical regions, still failing to reject the null hypothesis. But if I go to a 1%, now you can see that this would actually land over here, right? And this would land over here. And now I would fail to reject. Does that make sense to everybody? And I think that's kind of a difficult thing to realize with critical values, but it's a much easier thing to realize with p-values. So that's another reason why p-values are established. So finding the p-value. So again, the 2.37 is locating that area and that area. We need to ask, what is this area right here? So we'll go equals, it's going to be norm dot dist negative 2.37 and then 0, 1. Oh, and I want to then say true. So it gives me that area there. Is it okay with everybody? Now that is the area only for this region. What do you know about this region? It's the same. So we need to double this number. So I'll say J2 times 2. And my p-value becomes 0.0177. P-value 0.01, I think it was 77 or 779. Okay. Alpha value. Okay. If alpha is 10%, okay, your p-value, okay, is this less or more than 10%? This is less, right? Okay. So at a 10%, you would fail to reject. Does that make sense? Okay. So we're always taking our p-value. Let's see here. Your p-value less than alpha. I'm sorry, you reject. Did I say that or did I fail? If your p-value is less, you reject. Okay. So p-value is less, so at 10%, we would reject. Okay. At 5%, is that still less than 5%? So you would still reject. But a p-value of 1%, is this less than 1%? It's not, right? Okay, 1.7% versus 1%. So here you would fail to reject. Okay? So remember what alpha is. Alpha is the acceptable level of type 1 error, which is the acceptable error that we're okay with in rejecting a null hypothesis that should have been accepted. Okay? And we're seeing here that at different levels of acceptance for type 1 error, you get different outcomes. It's not always the case, okay, with these three, okay? But generally, this will happen, okay? So what a lot of times what a researcher will do is they will just report this. They'll just tell you that the p-value is 0.0178. And then you will decide, as the audience, what decision can I then make about the null hypothesis at different levels of alpha? Which, if you think about what alpha is, it's a level of significance, which is the complement of our confidence interval, right? Our confidence level, right? Okay, so at 90% confidence, we reject. At 95% confidence, we reject. But at 99% confidence, I'm not sure. I fail to reject it. Don't have the evidence to do that. Does that make sense? Okay. Because of that we've talked about, like when you do a study, if you have an invested interest in the outcome of a hypothesis, whether you reject it or not reject it, you could do the study, and when you do the study, let's say at the beginning you choose alpha to be 5%, and for whatever reason you want to fail to reject the established mean, the null hypothesis, okay? But at 5%, your data says you got to reject it. But for whatever reason, you didn't want that. Maybe you've got some monetary ties to this study to prove something so that you can market it. So then the unethical thing to do is say, okay, let's go back and delete the alpha that we chose at the beginning, change it to 1%, and then we fail to reject. Does that make sense? And then you, as the statistician, are misleading your audience, which is obviously unethical. So because of that, a lot of times they just report the p-value, and they then let the audience decide the alpha that they want for their purposes. That kind of makes sense? Okay. And that's what this here at the end, what I was getting at with these last one. What's your decision? Well, my decision is ultimately based on what I chose for alpha. Okay. And then our conclusion we would write based on that decision. Is this okay? What I want to do, hopefully my voice is back tomorrow, but what I'd like to do tomorrow is start talking about the t-test, which is actually more applicable, okay? Because generally we don't know the population standard deviation. We don't know sigma, okay? The t-test takes that into account. In addition, we usually don't have very large samples, okay? Maybe sometimes we only have 20 buses that we can look at, okay? Maybe we only have 20 cities, or maybe if I'm doing a medicine, maybe like a experimental medicine, maybe I don't have a lot of people that are willing to take that medicine, or maybe I don't have a lot of people that have the illness that medicine is targeting. So the t-test would then take that into account. So we'll do that tomorrow. It's very similar to what we've been doing. Sigma gets replaced with the sample standard deviation, and then we just have to be worried about our degrees of freedom that will allow us to get the correct p-value back, or critical values, depending on the approach we use. So that's tomorrow. I told last class, we have between 9 and 10 sections. Now, they took that completely wrong. They thought chapters. They thought we were going to go through 10 chapters in the next 9 weeks. We've got about 9 or 10 sections to go. Some of those sections will take a day. Some will take 2 days. Some will take a week. But we're getting to the point where because we spent so much time so far, 9.1 through 9.3, talking about hypothesis testing and what it is collectively, that hopefully we can kind of skirt through the rest of hypothesis testing quickly, because we shouldn't have to relearn and reteach all those fundamental principles at the beginning of each of these sections when we do a different test. Is that all right? Should be an assignment open in Math Excel. Opened it yesterday. It's not going to be due. I know the cutoff date is tomorrow night. I'm going to move it back to Thursday, but just haven't got to that. So I'll do that tomorrow.